Let's begin our journey into complex numbers. And actually, you've been dealing with complex numbers all your life anyway. We'll discover why. Let's just start with this problem, solving a quadratic. And if I had this one, x squared plus 1 is equal to 0, we go x squared equals -1, and at this stage we'd say, hey, there's no solutions. The more correct answer is there's no real solutions. Now, what we often do in maths is whenever we come up with a problem like this and we can't solve an equation, we don't have a number to cover it, we create this new number. So the new number is I. So the new number is actually a letter. And I represents the square root of -1, or more correctly, I squared is -1. And I is what's called an imaginary number. It then allows us to go and solve this equation. X squared equals -1. We can now say, oh, well, hang on, that's all right, because x will equal plus or minus the square root of -1, which is I. So we now have answers to our equation. X equals plus or minus I. So every complex number actually has two parts. It has a real part, it has an imaginary part. So x plus iy. So the real part of z is x, the imaginary part of z is y when I call the complex number x plus iy. Note, both the imaginary part and the real part are real numbers. It's an imaginary part. I is the imaginary. The coefficient of it is real. Now, if they ask me a question like this, they tell me that, hey, z represents the complex number 3 plus 5i. If we had to find the real part, oh, the real part is 3. The imaginary part is just 5. It's not 5i. It's 5. Now, if the real part is 0, then z is an imaginary number. Or more to the point, it's a pure imaginary number. There is no real part to it whatsoever. So example of that, root 3i minus 6i. Basically, we just have one term, if you like, where it's something I. That would be our pure imaginary number. If the imaginary part is z, this is what you've been dealing with your whole lives. This is a real number. Or I suppose we could call it a pure real number. It has no imaginary part. Some examples of real numbers, well, we don't really need any because, as I say, you've been dealing with them your whole lives, but there's a few. 3/4, pi, e, -4, they're all real numbers. Now, every complex number has a complex conjugate. And we've seen that word before, conjugate, dealing with surds. Well, if you think about it, I is a surd. It's the square root of -1. Its conjugate, and the notation for conjugate is we put a bar over the z. It's going to be x minus iy. We change the sign on the imaginary part. So if my complex number is -2 minus root 7i, the conjugate is -2 plus root 7i. So how does it all fit together? So real numbers is what we've been dealing with. And just a reminder of our set of real numbers. Real numbers are simply numbers that can be placed on the number line, or to give it its more correct name, the real number line. If it can be placed on that, it's a real number. The symbol for the set of real numbers is the hollow R. So in our set of real numbers, we have rational numbers. The symbol for that, the hollow Q. Q stands for quotient. And then we have irrational numbers. So real numbers are either rational or irrational. We don't actually have a symbol for irrational numbers, but sometimes, very rarely, don't see it often at all, but if you had to describe the set of irrational numbers, you could write it like this, R\Q. So you say, well, it's all the real numbers, but not including the rational numbers. So you get the irrational numbers. Inside our set of rational numbers, we have fractions. What do I mean by fractions? I'm talking about the things that can't be expressed as a whole number. I mean, a whole number is a fraction technically. 7, you could write a 7/1. So it is a fraction. I'm not meaning that when I say fractions here. I'm talking about the ones that can't be simplified down to be a whole number. And then we have this set, integers. They are the ones that can be simplified down to a whole number. The symbol for that is the hollow Z. Why Z? Well, it comes from the German, Zahlen, which is German for numbers. Inside our integers, we have the natural numbers, sometimes called the counting numbers. Symbol for that one, N. But then we also have that wonderful number 0, which is the funny number. It's actually a number, but 0 sort of sits by itself. We do call it an integer though, because you could write it as 0/1. And then overlying these, we have the negative numbers. Now, we don't have negative 0, so you notice it doesn't overlap there, and we don't have negative natural numbers because the counting numbers you start at 1. But we could have negative fractions, we could have negative integers, and it is possible to have negative irrational numbers as well. That is what we have been dealing with. But that set of real numbers actually sits inside the set of complex numbers. Complex number C. So real numbers, the imaginary part is equal to 0. And over here we have the imaginary numbers, well, pure imaginary numbers, and that's when the real part is equal to 0. Then, of course, it is possible to have numbers that are a mixture of the two. That would be the ones that's sitting outside these two blue rectangles. So if you had something like 3 plus 5i, well, that's still in the set of complex numbers. It's not a pure imaginary number. It's not a pure real number. It's just a complex number. Okay. The interesting thing about imaginary numbers, they can't be ordered. If you cannot place the number on the real number line, then you can't order it. You can't say this one's bigger than that one. Because when we start talking about the other complex numbers, the ones that aren't real, which one's bigger? 5 plus 2i or minus 5 minus 2i? Well, you'd be tempting to say, well, surely the positive 5 plus 2i is bigger than the negative 5 plus 2i. But what if I said it this way? What about 5 minus 2i and negative 5 plus 2i? Which one's bigger? Well, hang on. Both got a negative bit and a positive bit. Which one's more important? Is the real part more important than the imaginary part? You can't order them. So you can only order real numbers. Well, how do we play with these new numbers? Basic operations. And as I said before, it's simply a surd. And we know surd arithmetic. We know how to handle surds, so we already know how to handle our complex numbers. So addition, you could think of it like surds. You could also think of it just like algebra. Add like terms. So minus 4 minus I. Subtraction, again, it's just like algebra. 12 minus 5i. Multiplication. Okay, well, we've seen binomial products. There's a little difference though with this one. Because when I expand it out, I will get this term at the end here, minus 6i squared. Remember, I squared represents negative 1. That's actually a real number. So when we tidy that one up, we've got to remember this minus 6i squared, it's not a different term. Right? You can only add like terms. It's actually a like term. It's a real number. So it will add with the other real number. So whenever you see I squared, we change the sign on the number. It'll be minus 32 plus 6, we get negative 26 plus 32i. Division, also known as realising the denominator. So with surds, we rationalise the denominator. We turn the denominator into a rational number. With complex number, we want to realise the denominator. We want to turn the denominator into a real number. But the idea is still the same. We multiply top and bottom by the conjugate, because we know that when we multiply conjugates together, we'll get the difference of two squares, although in this case, because of the I squared, we actually get the sum of two squares. So we get 64 plus 4 on the bottom. And so that gives us minus 38 plus 16i over 68, breaking up into its real and imaginary part, minus 19 on 34 plus 8 on 34i. Unlike surds though, remember when I said things like, what's the sine of 45? 1 on root 2. And I said, well, we're perfectly happy to leave root 2 on the bottom. There's nothing wrong with that. The same does not apply here. We don't leave I on the bottom of a fraction. Why do we rationalise denominators? It's for the sake of comparison. So with that sine of 45, I'm getting 1 on root 2. I don't need to make that a rational number on the bottom because I'm not comparing it to anything. I'm just using that number. Whereas when we're talking about these complex numbers, I do need to realise the bottom. I might want to compare that complex number to another complex number. Now, speaking of conjugates, some basics, how we play with conjugates. It's fairly straightforward. If you want to find the conjugate of two complex numbers added together, you can do it either way. You could add them together first, then find the conjugate, or you could find the conjugate of each individual one, then add them together. You will get the same answer. Same with multiplication. Same with division. Same with subtraction as well, but I don't think I put that one up there because really addition and subtraction are the same thing. This one's interesting. That's the one that I said before. before about when you multiply a number with its conjugates, you end up with the sum of two squares. The real part squared plus the imaginary part squared. That's a very important relationship. In fact, here's where it becomes very useful. If I want to find the reciprocal of a complex number, well, if you think about it, all I've got to do is multiply top and bottom by the conjugate. And then I've got a neat little way of finding the reciprocal of a number. If I want to find the reciprocal of 1 on 4 minus 3i, okay, I know I'm going to end up with the conjugates, 4 plus 3i, over that sum of two squares, 16 plus 9, which is 25. That's why we just turn a complex number upside down. What about equations then? Obviously we're going to be doing a lot of equations. How do we deal with complex numbers and equations? If two complex numbers are equal, the real parts are equal, the imaginary parts are equal. Remember, there's no overlap of those two sets. So the real part must equal the real part and the imaginary part must equal the imaginary part. If I'm solving this sort of simple equation here, I know straight away, well hang on, A1 must equal A2 and B1 must equal B2. It's the only possibility, because there is no overlap. It's very similar to the quadratic identities and things like that we did, where we said, oh, the coefficient of x squared must equal the coefficient of x squared. Same idea. Well, let's solve this equation then. I'll expand the left-hand side out, because that'll make life a bit easier for me. But now I just have to say, well, all right, the real part will equal the real part, and the imaginary part will equal the imaginary part. I've got some simultaneous equations to solve. X is 2 on 13. Subbing that in, we get y is 16 on 13. So we found x, we've found y. Simultaneous equations, still the same idea. Remember, I is not a pronumeral in this case, it's the imaginary number. It is a number. So it's z and w we're trying to find here. We want to make the coefficient of z the same or the coefficient of w the same. The idea doesn't change. We still do it the same way. I've made the coefficient of w the same. I've made them both 2i. Now I've multiplied the second equation by 2. So I can eliminate, and I get that 3z is 2 plus 5i, z is 2/3 plus 5/3 i. Now I substitute back in and work out what w is. A little bit more involved than our normal simultaneous equation, because we have to worry about real parts and imaginary parts, but we end up with, well, first of all I get what 2iw is. Now I want to divide everything by 2i. Oh, 10 over 6i. Alright, that becomes minus 5/3 I. And we have our two answers. 2 minus 5/3 I, 2/3 plus 5/3 I. Well, that's interesting. They became conjugates. Well, I suppose when you look at the equations, that's not unexpected, because there is some symmetry in those numbers there. So there's just a start of our journey into complex numbers.